Okay, hi folks. I had a lecture with you earlier this morning, and it was the first lecture on January 5th. And because we spent about 20 minutes talking about the syllabus, and also there was a room change issue that was a mistake on my behalf. We lost about 20 minutes, and towards the end, I came across a review slide, which is from your differential equations, which you took maybe last year or 2 years ago in your second year from the math department. I think it's about time we go and review that because this is going to pop up a lot in different in vibrations course. So I'm calling a review of second order linear time invariant ordinary differential equation for a reason that you see in just a minute. So let's go ahead. All right. So that's what I have. Notice that the thing that all of these have in common, first of all, they are second order differential equation, x double dot. X double dot means second derivative of x with respect to time. X dot means first derivative of x with respect to time. So this is second order, and it's a linear differential equations, all three of them, and they all have constant coefficients. Constants here, constants there, and constants there. These are very easy to solve, okay? And what I want to do is I want to go through the solution of these three equations, which will lead into different outcomes, and then come back and discuss about the general setup, because in this course, when we treat a single degree of freedom system, our differential equation is going to be like this. The mass second derivative, acceleration, plus the damping coefficient, first derivative, if there is damping, plus the stiffness of the spring times x equal to 0. And look at the similarity between these. Are identical except that the values of m, c, and k are different. Okay, so the reason that we want to talk about this, review it for you, is because for the single degree of freedom system that we're going to be using for 10 weeks in this course, or maybe 8 weeks in this course, they're going to be like that. It's going to be linear, second order, time invariant differential equation. Okay, the right hand side, incidentally, I made it 0 here, but it can be a function of time also. All right, so let me start with the first equation, namely the one that you see there. Okay, so let's go ahead. All right, let me start with the first one. So we have 3x double dot. Oh, sorry, not 3x double dot, it's x double dot. Forget about this. I don't know where the eraser is for this. So we have x double dot plus 3x dot plus 2 equal 2x equal to 0. So what we do, we look for a solution of the form x of t equal to e to the st. So this is your guessing solution. We take this and we plug it in. So if you do that, x dot of t will be s e to the st, and x double dot of t is going to be another derivative of this, which is going to give you s squared e to the st. Now, if you take these and you dump it in that equation, you're going to get s squared. Oops. You're going to get s squared e to the st plus 3s e to the st plus 2 e to the st equal to 0. Now notice that I can factor e to the st, so I'm going to get s squared plus 3s plus 2 uh, e to the st equal to 0. Now, e to the st is not 0, so we can divide through, and I get s squared plus 3s plus 2 equal to 0. And this is what your differential equation professor said, characteristic equation. Characteristic equation. So you have to solve it. This is algebraic equation. There's no more derivative there. And you use the formula for quadratic, or if you can factor it, you just do it based on what you know from your high school stuff. Plus 1 equal to 0. Remember, in general, we can use the formula for quadratic that I have it in the previous slide. Uh, if you have as squared plus bs plus c equal to 0, the expression for s is minus b plus or minus square root of b squared minus 4ac over 2a. But if you can factor it, there's no need to use that, and you're going to get two values, s equal to minus 2 and s equal to minus 1. Therefore, based on our guessing solution, we have e to the minus 2t and e to the minus t both being solutions of that equation. And the general solution is a combination of these because of the linearity, the stuff, superposition. As engineers, you're used to that term. E to the minus 2t plus c2 e to the minus t. This is the general solution to that second order linear time invariant differential equation. Okay. Now let's go and do the second problem. The second problem looks very similar with the exception of the coefficients. So we have x double dot plus 4x dot plus 4x equal to 0. And once again, you make a guessing solution of the form x of t equal to e to the st. So x dot is s e to the st. X double dot is s squared e to the st. You take these things and dump it in here, and you factor e to the st. I'm not going to do all the steps here. I'll just write it down. You get s squared plus 4s. Please make sure you take these things and put it in there, and you get what I have. 4 e to the st equal to 0. Now, e to the st is not 0, so I can just throw it away. So we have s squared plus 4s plus 4 equal to 0. When I say throw it away, it means I can divide through by e to the st because it's not 0. Okay? Now notice that this can be factored also, s plus 2 times s plus 2. Notice that in the previous problem, it was s plus 2 times s plus 1 equal to 0. But here, these factors are identical. So one of the roots is immediate. The other root is identical to the first one. And if that is the case, your differential equations professor told you that one solution is the usual e to the minus 2t, and the other solution, well, it's no good if you use again minus 2 because you're going to get exactly the same solution. But when you have repeated roots, the other solution, based on what they taught you in differential equation, is t times e to the minus 2t. Okay? So the general solution becomes c1 e to the minus 2t plus c2 t e to the minus 2t. Okay? Now, this is the general solution to this differential equation. We are ignoring all the initial conditions. C1 and C2 depends on the initial conditions that we are ignoring in this problem. So we're just looking at the differential equation, how to do the recipe for solving these things. The third problem that I'm going to do is, again, same thing, except the coefficients are different. So we have 4x here, 4x dot, sorry, plus 5x equal to 0. Now, if you look for the solution of the form x of t equal to e to the st, again x dot will be s e to the st, and x uh, double dot will be s squared e to the st. So if you take these things and dump it in here, you're going to get s squared. Go back here, lost the page. S squared plus 4s plus, this is s, okay, plus 5 equal to 0. The problem is that this does not have any real roots, so I have no choice but to use my quadratic equation. I mean, you can factor it if you want, but I'd rather use the quadratic equation. So there is your A is 1, there is your B, and there is your C. So B is 4 and C is 5. So minus B, so it's going to be minus 4 plus or minus square root of 4 squared minus 4, wow, minus 4 times A, which is 1, times C, which is 5, over 2 times 1. Now, if you clean this up, you're going to get minus 4 plus or minus. Now, up there, you have 16 minus 20. 16 minus 20, so it's going to be minus 4 underneath the radical, minus 4 divided by 2. Now, this is minus 4 plus or minus 2j over 2. Now, j means square root of minus 1. Okay, so if you clean this up, you get two roots, complex roots. So it's going to be minus 2 plus plus, okay, plus or minus j. Good. So there are two solutions to this, but they're both they're complex, obviously, complex conjugate, as you can see. So one of the solution is minus 2 plus 2j plus j, not 2j, plus j, and the other one is minus 2 minus j. So the solution in complex form of the form e to the minus 2 plus j, remember it's s times t, and e to the minus 2 minus j times t. Now, these are the complex form, but remember from this basic Euler's formula, there's something called Euler's formula. So e to the j theta or I theta, whichever you prefer. Some people you like to use I equal to square root of minus 1, is cos theta plus j sine theta. It's called Euler's formula. You can convert this thing into sine and cosine. So this one will be, you can write it as e to the, this, first of all, write it like that, minus 2t e to the plus j times t. This is times that. And this one will be e to the minus 2t e to the minus jt. So this formula, you're going to apply it to the second part, this part. Okay, so let me go and do that for you. So one of the solution is going to be e to the minus 2t cosine of t plus j sine of t. The other one is going to be e to the minus 2t cosine of t j sine of t. So minus. Right. Let me actually be a little bit more careful here. Let me write it the long way. It's not wrong, but I'm going to write it the long way for you. So it's going to be e to the minus 2t. Now remember, it was multiplied by e to the minus jt. So if you're going to use that formula, instead of t, instead of theta, use minus t. So it's going to be cosine of minus t plus j sine of minus t. Terrible screen. Now that's why cosine of minus t is the same as cosine of t, and sine of minus t is minus sine of t minus j sine of t times e to the minus 2t. And this is what I wrote for you in one step. This is the same thing. I wrote it in one step, but that's where it's coming from. Now, this and that are both solutions, okay? However, if we are interested in the real solution, we can add these up, okay? So if we are interested in real solution, we can add these up. So you're going to get e to the minus 2t. Now notice that when you add these up, the term sine disappears, times cosine of t times 2. This is when you add them up. When you subtract them, the cosine disappears, e to the minus 2t, because it's common, that's not going to get anywhere. And this minus that is going to be 2j sine of t. However, if because it's a somehow I almost oh yeah okay, so we were down here, that's fine. Um, oh, because this is a linear equation, if this is a solution, half of it is also a solution. So we can say you divide the thing by 2, so you're going to get oh my god, what happened? E to the minus 2t cos t constant c1 plus, because this is a solution, 1 over 2j is also a solution. J is a constant. So e to the minus 2t sine of t multiplied by c2 is also a solution. So this is the solution to that equation that I gave you. So I gave you 3 different forms of the equation. One of them had 2 distinct roots. When you found the characteristic equation that 2 distinct roots, easy. When the two roots were not distinct, they were the same. One of them I wrote, the other one I multiplied that by t in the front of the exponential, and I got my solution. And finally, if the solutions are complex, then you have to, and if you're interested in the real solution, and we are in this course, so what you do, you find the complex expressions, and you add the Euler's, you use the Euler's formula in order to convert it into the real solution that you're looking for. Okay, let me finish this thing by going here. In general, if this is your mass spring damper system, you find the you look for a solution of the form e to the st, you plug it in, solve for the characteristic equation, and you might run into one of these 3 conditions. In other words, distinct distinct real roots, uh, identical real roots, which means 2 of them are the same, or complex roots. And you have to find the characteristic equation. You make it two distinct real roots. You make it identical root or complex root. And that is what I wanted to say this morning, but we ran out of time. Okay.